Hi class. Hi, non-existent for the moment class with 0 people watching. Hopefully I'll get somebody watching later. Um, the next step of what we're going to learn is about polyprotic acids. Hey Timmy. Some acids have more than one ionizable proton, so each successive ionization is a weaker acid with a smaller Ka value. Uh, Example of that would be phosphoric acid. Phosphoric acid has 3 ionizable protons. So each one that comes off has a, a Ka value that's about 1,000 times smaller than the one preceding it. Um, so final final summation of that is that you can calculate the pH of polyprotic hyraxia. You can calculate the pH of polyprotic acids by basically focusing on the highest Ka value. That's going to be the primary determinant of how many protons are in solution, because the next dissociation produces something like 1/1000th of the number of protons that the first dissociation produces, so it's essentially negligible. So it says in the textbook, for most polyprotic acids, calculations of H plus are safely based on Ka sub 1, meaning the first dissociation, as long as Ka sub 2 and sub 3, I put Ka in 1, no actually it is 1, as long as Ka1 and 2 differ by at least a factor of about 1,000. On page 693, they do a calculation involving a polyprotic. It's actually a diprotic acid. It asks you to calculate the pH of a 0.02 molar solution of oxalic acid. Oxalic acid is an acid, hi, Saviwe, I think it was. Um, Oxalic acid is found in some foods. I think it's found in grapes, for instance, and it's actually the reason why things like grapes are bad for dogs, because the dog's metabolism can't handle oxalic acid. Oxalic acid forms crystals in the kidneys of animals that are unable to metabolize it. Well, in fact, if we drink ethylene glycol, the alcohol dehydrogenase in our system will oxidize the oxalic acid and turn it. It'll oxidize the diol, ethylene glycol, into oxalic acid. Oxalic acid forms crystals, and you destroy your kidneys. The nasty thing about ethylene glycol is that it's sweet. So if a dog gets a hold of it, they'll drink it and they can poison themselves with it. So that's why you don't leave ethylene glycol sitting around. There's pets around anyway. And you don't feed grapes to dogs for the same reason. So anyway, oxalic acid, 0.02 molar solution. It has a Ka and K1, a K1 and K2 value that are listed there. Actually, they're not listed here, but you have to look them up. Oh, it's on the facing page. It has it, and they're asking you calculate the pH, and then for part B, calculate the concentration of oxalate anion. So the way to do this is this day 13 or day 12 now? I can't remember. Today's day 12. Period 4. So there's a dissociation. These are 2 ionizable protons. So the first one comes off, and you get the oxalate anion and 1 proton. The original concentration is 0.02. We're going to do a little ice table to help us keep track of everything. A certain amount of it dissociates, so at equilibrium you have 0.02 minus whatever has dissociated. Initially you have no oxalate, then a certain amount X appears, and at equilibrium you have X. And the same thing with the H plus ion. So you can set up an equilibrium equation. Ka is equal to products over reactants, which is the oxalate anion concentration times the amount of protons produced divided by the original concentration or the equilibrium concentration of the oxalic acid. And that's going to be represented by x times x over 0.02 minus x, and all of that has to equal 5.9 times 10 to the minus 2. My favorite way of doing these calculations is to use the quadratic formula because it just gives you the most accurate result, and because we have calculators, if you have to use the quadratic formula, I know it's a real pain. That's why they developed the approximation method, because trying to enter multiple decimal numbers into the quadratic formula is time consuming and it's easy to make a mistake, and if you're writing an exam it can get you into hot water because you end up wasting a lot of time. So anyway, 5.9 times 10 to the minus 2 times 0.02 minus x gives you x squared when you do a cross multiplication to turn it all into a straight line. And then it comes out to a trinomial x squared plus 5.9 times 10 to the minus 2x minus 1.18 times 10 to the negative 3 equals 0. If you enter it into your calculator quadratic solving function, you'll get two answers, 1.57796,864 times 10 to the minus 2, and you'll get negative 7.47796 times 10 to the minus 2. So this is the correct answer. This is not plausible. You keep the one that's plausible, and then you calculate the pH because that's what they're asking for. So let's erase the top here. Since pH is equal to negative log of the H plus concentration, which in this case equals 1.577, etc., times 10 to the minus 2, we get a pH equal to 1.80 after sig fix. You get 1.8019. But you always reduce it to two decimal places when you report pH. Now, the concentration of the oxalate ion, as is asked for in part B, is dependent upon the second ionization. Hi, Aini. Okay, so there's a second dissociation. I'm calling oxalate ion the one that has one proton in it, and also the one that has no proton. So I should have said hydrogen oxalate, and now the full oxalate now where all two protons come off. So let's just write a little note. The concentration of oxalate ion, and that would be C2O4 with a minus 2 charge. Just realized I didn't put negative 2 there, I only put a negative 1. So bonus for me. It depends on the second dissociation. Which is K sub 2, and it is equal to 6.4 times 10 to the negative 5. It's a pretty weak acid on that second dissociation. But what we're looking for is the oxalate anion concentration. So we start with hydrogen oxalate, C2O4 with a minus 1. We'll draw a nice table for that as well. The second dissociation will proceed to give you C2O4 with a negative 2 charge and produce yet more hydrogen ions. We know that there's that much of the hydrogen oxalate, 1.577, etc., times 10 to the minus 2, yet more dissociate. This dissociates to produce the oxalate anion, so 1.577, etc., times 10 to the negative 2 minus x. This starts off at 0, plus x appear, and x is present at equilibrium. This starts off also at 1.577, etc., times 10 to the minus 2, plus a tiny bit more appears because of the second dissociation, but it's entirely negligible because the value of Ka sub 2 is about 1,000 times smaller than Ka sub 1. But what we're asked for here is to find out the oxalate anion concentration. Hi, Marvin. So the Ka sub 2, which is equal to 6.4 times 10 to the negative 5, is also going to equal to the H plus concentration total times the concentration of oxalate anion over hydrogen oxalate anion concentration. And that gives you 1.577, etc., times 10 to the minus 2 minus x times x all over, no, it's not minus x, it's plus x. Sorry about that. Yeah, because there's a plus x here. And on the denominator, you have 1.577, etc., times 10 to the minus 2 minus x. So when you solve that, again using your quadratic formula, plugging in the values into your calculator, and when you on most scientific, no, in fact on any scientific calculator worth its salt, you're going to have that quadratic function, and you can plug in the numbers, and it'll pop up two values, x1 and x2, and you pick the most plausible one of the two, because you're often going to get a negative value, but you can't get a negative concentration. You can only get positive concentrations. So the trinomial that you get from this equation looks like this: x squared plus 1.584, 368, 64 times 10 to the minus 2x, minus 1.00989993 times 10 to the negative 6, all that equal to 0. When you plug it into your calculator, you'll get the following two answers. You can corroborate by doing it yourself, and I encourage you to do exactly that. So you get something to the 10 to the negative 5. The other answer would be negative 1.5907, blah, blah, blah. We don't care because it's negative, so we're not even going to use it. This is the correct answer. So the pH, sorry, it's not the pH you're looking for. You're looking for the concentration of C2O4 negative 2, the oxalate anion. It's going to equal to the value of X, which is plausible, which would be that one. So concentration comes down to 6.3 times 10 to the negative 5 molar for the oxalate anion. Problem solved. The next section brings up bases, weak bases. Now, weak bases don't always necessarily produce hydroxide right off the bat. What they do is they pull a proton off water and thereby produce hydroxide. So ammonia, for instance, is not releasing OH into solution. What it's doing is combining with water, and the nitrogen atom has a lone pair on it. That lone pair pulls a proton off the water, and the ammonia turns into ammonium, and then the water that's had the proton pulled off of it ends up becoming hydroxide. So adding ammonia to water, because ammonia is a gas, but it's very highly soluble in water. When you add ammonia to water, you get hydroxide in the solution. And the base dissociation constant that they describe for that is called Kv. It's the counterpart of Ka. Interesting thing, when you multiply Ka and Kb for the conjugate base of the acid, you'll get Kw. So Ka times Kb always equals Kw, which equals 10 to the negative 14. So the Ka would apply to ammonium, which is the conjugate acid of ammonia, which has Kb applied to it. Okay, so when you multiply those two of the conjugate acid and base pair, you will get the Kw in aqueous solutions. On practice example page 695, they ask you to compare the strength of various solutions. Which of the following compounds should produce the highest pH as the 0.05 molar solution? Pyridine, methylamine, or nitrous acid? And then you have to compare the the Kb values. Sometimes they only supply the Ka value, so you can calculate the Ka value. As it turns out, the Kb values are all listed here. So pyridine, it's 1.7 times 10 to the minus 9. Methylamine is 4.4 times 10 to the minus 4. And nitrous acid is 4.5 times 10 to the minus 4. Those are all Kb values. No, Ka, nitrous acid, it gave me the Ka value. Sorry, I looked up nitrous acid because they're asking for the Kb. So they only supplied the Ka value for nitrous acid. Where is it? So let me show you. We got pyridine. Yes, Mama? What is it? Methylamine. Nitrous acid. So the Kb values you'll get are 1.7 times 10 to the minus 9, 4.4 times 10 to the minus 4, and for nitrous acid, I was only able to find the Ka, which was 4.5 times 10 to the negative 4. So how do I find the Kb? Well, Kb is equal to Kw over Ka. In this case, it's 10 to the negative 14 over 4.5 times 10 to the negative 4. So the Kb for nitrous acid is 1 exponent negative 14 divided 4.5 exponent negative 4. You get 2.2 recurring. 2.2 recurring times 10 to the negative 11. So that's not its Ka, Kb. Kb is 2.2 recurring times 10 to the negative 11. So the strongest base is the one with the biggest number. This is the strongest base, strongest weak base in this list. So methylamine will have the best effect. Now, whenever you do organic chemistry, one of the big things that they teach you is the importance of the solvent that you're conducting the chemical reaction in. Solvents can shield things from happening, or they can promote things into happening, either by stabilizing the formation of ions or preventing the formation of ions, or even you can have solvents that are aprotic, so they don't catalyze certain side reactions. There's a whole bunch of things that you have to take into account when you want to promote one type of chemical reaction and suppress another. And if you have a good working knowledge of solvents and the effect they have on different reagents, you can actually become a competent organic chemist. It's a challenging field. I mean, anybody can learn organic chemistry, but to learn it well, that's another story. Page 696. Practice exercise. It says a solution of ammonia in water has a pH of 11.17. What is the molarity of the solution? Okay. Now, NH3 aqueous NH3 aqueous gives you a pH equal to 11.17, and what they're saying is, what is the NH3 concentration? Now, we know that pH plus POH always has to equal 14, and so the POH in this case has to be 14 minus 11.17, which gives you 2.83. Which allows you to calculate the OH minus concentration. OH minus concentration is going to equal to 10 to the negative of 2.83. And that gives you an OH minus concentration of 1.479 10839 times 10 to the power of negative 3 molar. Kb for ammonia is 1.8 times 10 to the negative 5. So if we let X equal the initial ammonia concentration, we can set up an ice table that demonstrates the following reaction. So ammonia mixes with water. It abstracts a proton from water, generating the ammonium ion and hydroxide. Make an ice table, call this X. You know that the concentration at equilibrium of hydroxide is 1.479, etc., times 10 to the negative 3. So you know that this same amount was abstracted from the original ammonia. So that equilibrium is going to be X minus 1.479, etc., times 10 to the minus 3. So you can set up, and also this will be the same number, 1.479. So you set up an equilibrium concentration, KB, and the only thing you don't know is X. So you set it up like this, KB, which equals 1.8 times 10 to the negative 5 for ammonia, also equals, in this instance, 1.479, etc., times 10 to the minus 3 all squared over X minus 1.479 times 10 to the minus 3, and you get 1.8 times 10 to the minus 5. X equals 2.214. 558 times 10 to the negative 6. And so your original concentration of ammonia comes out to 0.123021421 molar. You're only allowed to report it to 2 sig figs, so you're going to say 0.12 molar as your final answer. That's your original ammonia concentration. Sometimes you get the conjugate base. Okay, first of all, let's reiterate here. The conjugate base of any strong acid has no pH activity. So you know your strong acids. No so-chlorobri. I taught you the mnemonics. So nitric, sulfuric, chloric, perchloric, hydrobromic, hydrochloric, hydriodic. Those are the 7 strong acids. So the counterions of all those 7 strong acids have no pH effect. So chloride ion, because it's the conjugate base of hydrochloric acid, has no effect on pH. Nitrate anion, because it's the conjugate base of nitric acid, no effect on pH. However, if you have a weak acid, the counterion of a weak acid does have an effect on pH. So take any weak base, like say a weak acid like acetic acid. The conjugate base of acetic acid is the acetate anion. So let's just draw that for a moment. Suppose you have the vinegar, acetic acid, CH3COOH. It dissociates to give you the acetate anion and a proton. Okay? This is the acid. This is its conjugate base. Turns out, if you took a solution of sodium acetate, NaCH3COO-, it could interact with water. It'll abstract the proton from water. Okay, once it dissociates. Okay, once it dissociates, that's the first step. It'll dissociate into sodium cations and acetate anions. Okay, then the acetate anion is still sitting around in the water, and it can interact with the water, pulling a proton off water so that it reconstitutes acetic acid. And then you get some hydroxide. So if you take a solution of the counter ion of a weak acid, it will demonstrate basicity. Sodium acetate is basic. It's the reason why when you eat salt and vinegar chips, your mouth turns white and all your skin peels off on the inside of your mouth the next day, because it's corrosive. In fact, it might be a better cure for sore throat than taking lozenges, because it basically corrodes the inner layer of your mouth. You ever notice? The next day you can peel pieces of your skin off, because the sodium acetate is actually corrosive. So this is that's the base. It's a weak base, obviously, but it has a measurable basicity. Let's do a question where you have to use that idea. On 699, it says, it's practice exercise. Which of the following anions has the largest base dissociation constant? Nitrite, phosphate, or azide? Anyway, you got to look up the values of Ka, because they don't give you the Kb's. Then you do the Kw over Ka to give you the Kb. Turns out that the strongest base of those three is phosphate. You can actually buy phosphate anion. You can buy trisodium phosphate, they call it. You can buy it at Canadian Tire or Home Depot, and they use it for cleaning walls. So it's also the basis for washing soda. Actually, in washing soda they use carbonate. The stuff you put in your dishwasher to make sure the dishes come out clean is basically potassium carbonate. That's washing soda, or sodium carbonate, because the carbonate anion has a basic properties. Sometimes they'll throw in percarbonate. They add an extra oxygen in there, so it has some oxidizing capacity, and it makes your dishes squeaky clean, because it oxidizes the oils that are resistant. Because you can't have suds, obviously. You can't have suds in your dishwasher, or else it turns into if you ever made the mistake of putting regular detergent in your dishwasher, it makes like a bubbly mess. You have to have non-sudsing detergent. Well, let's do part B of 699. Let me read it first. It says, the base quinoline has the following structure. Its conjugate acid is listed in the handbooks as having a pKa of 4.9. What is the base dissociation constant for quinoline? So here's quinoline. And this nitrogen atom has a lone pair, so it can actually pull a proton off water, and when you do that, you'll get positive charge on the nitrogen. Whoops, the daisy. There we go. And you get some hydroxide as well, because it's pulled the proton off the water. So they give you the Ka value for it, they want the Kb, so to do that, to find that out, you get negative log of Ka is equal to pKa, which equals 4.9 in this case. So whenever you see P, you're taking the log of it. So 10 to the negative 4.9 is going to give you the Ka. And it turns out that Ka for this substance is 1.2589, 2541 times 10 to the negative 5. And since Ka times Kb is equal to Kw, therefore Kb is equal to Kw over Ka, 10 to the negative 14 over 1.258, etc., times 10 to the negative 5. So Kb equals 7.9 times 10 to the negative 10. It's a very weak base. Let me see if we can do one together. They don't have a lot of worked out problems. I've already posted these notes, so here's what you can do. Let's see if you're smart enough to do this. weak acids. I'll give you one each. A weak acids problem and a weak bases problem. Because strong acids and bases are trivial. Try 1659 and 1675. 1659 and 1675. 1659 and 75. All right, so homework. Give that a go. I'll post the answers tomorrow. And you know what? If you want to really practice, try doing it by the approximation method, the quadratic formula method, and if you're feeling particularly confident, you can try the iteration method. Okay, so it's 3 different methods. You can solve it. You should get very similar, if not identical, answers. Okay, see you tomorrow.